So what we're going to do here is use the opportunity of this video to really go through the problem set that I've posted for chapter 19 and do some of the problems together. So here we're starting with the first question. So here I'm going to pull up that, which is to predict the products of the reaction of phenylacetaldehyde, and I'm going to do it just for this case with the following reagent. So the first one asks you, the first question is, can we draw the structure of phenylacetaldehyde? Okay, so acetaldehyde by itself is going to look just like this. Okay, so just a CH3 attached to an aldehyde. And when I say phenylacetaldehyde, what I mean by that is just to add acetaldehyde. So phenylacetaldehyde now just adds that phenyl group to the parent acetaldehyde, which is this structure here. And then if I want to treat this with NABH4 followed by H3O+, the question becomes, what product will that form? So NABH4 is a source of the H- anion. So let's just move over here and zoom in a little bit. NABH4 is the source of the H- anion, and that H- anion adds as a nucleophile to attack this carbonyl, push up electrons, and form our favorite species here, this tetrahedral intermediate. Again, this is general for all nucleophilic additions to carbonyls, that they're going to lead to the formation of this tetrahedral intermediate. In this case, it's going to be anionic with a negative charge on the oxygen, again, coming from pushing up of these electrons. This anionic oxygen now picks up in the separate step, picks up a proton from the H3O+, and then these electrons get pushed onto the oxygen to neutralize that positive charge, so that the net result at the end is this neutral alcohol species as well as water. So again, I start with an aldehyde, and what I can form with the treatment of NABH4 is a primary alcohol. So again, NABH4 reduces aldehydes to primary alcohol through the introduction of an H-, which does nucleophilic addition to the carbonyl. The second question is, what happens if I treat phenylacetaldehyde with a Des-Martin reagent, so DMP? This is the same thing as saying DMP, which is our Des-Martin periodinine. And when you treat an aldehyde with DMP, nothing happens. Absolutely nothing happens. What does DMP do? DMP is a great reagent if I had, for example, a primary alcohol like this, and I wanted to create the aldehyde, then I could treat that with DMP to go in this direction. However, if I take this aldehyde now and treat it with DMP, it will sit around and look at each other forever, and there is going to be no reaction. Okay, the book answer key, if you have that or access to that, says that a carboxylic acid is formed. That's almost certainly not true. Okay, DMP looks at the aldehyde and does nothing. DMP, again, just to remind us, is a great reagent for forming aldehydes. Now, what does C here? C asks, okay, we're going to skip C for now, just in the interest of time and making this brief. But part D says, what happens if we treat phenylacetaldehyde with methyl magnesium bromide or methyl Grignard reagent, this guy here, and that acts as a source of CH3-, like all Grignards and all organometallics. Again, that's a effective CH3- because the C metal bond is so polarized with electron density on the carbon, again, because now the carbon is more electronegative, so that polarizes the electron density in that direction. And what that does for us is it allows the CH3- to attack the carbonyl here. Once again, I'm going to form my favorite tetrahedral intermediate with an O-. Here the methyl group has added. I pick up a proton from the H3O+ now in my separate step to form, in this case, a secondary alcohol. So in the NABH4, for example, the H- gives us a primary alcohol, aldehyde to primary alcohol. When I take a Grignard reagent, the CH3-MgBr gives us an aldehyde to secondary alcohol through the addition of that methyl reagent in that case. Now, what I can do is look at my part E, which asks what happens if I take my phenylacetaldehyde and I treat that with HCl catalyst now and methanol. And every time where I take a carbonyl compound and I treat that with an acid catalyst, every time what I'm going to form in the first step is I will protonate my carbonyl to generate this intermediate here, this protonated carbonyl intermediate. This protonated carbonyl intermediate now is susceptible to nucleophilic attack by methanol. Here the oxygen of the methanol adds as a nucleophile to this carbonyl. I push up electron density like this and I form this tetrahedral intermediate. The mechanism for acid catalyzed nucleophilic additions is always slightly different than the mechanism for the base catalyzed reactions, and that's mostly because under acid conditions I can never get negative charges, okay? Never get negative charges under acid conditions. And in order to avoid getting those negative charges, what I need to do is pre-protonate this oxygen by picking up a proton. And again, my nucleophile that adds is going to be neutral, which means that my initial charge here is going to be positive. Alright, now the Cl is going to pull off this proton here to form this intermediate, which is a hemiacetal. This hemiacetal is going to undergo further reaction now with H plus to form an OH2, and the reason it does that now is this now becomes a good leaving group. Water is a good leaving group now in this case. And that water gets displaced by another equivalent of the methanol. I kick off the water, and now have another protonated methanol nucleophile that gets deprotonated by the Cl- to give me this final acetal formed product. And again, overall what I've done here is I've added 2 equivalents of methanol under acid catalyzed conditions to form my acetal compound. And it says, it's specific here to say 2 CH3OH. It's 2 equivalents of the methanol that are being added again under acid catalyzed conditions to generate this target product. If I look at F, I take my phenylacetaldehyde and I treat this with this H2 and NH2 and KOH. This is Wolff-Kishner reaction conditions. You are not responsible for the mechanism of the Wolff-Kishner reactions, but it is important to understand that what these conditions do for me is it allows me to start in the case where I have a carbonyl, in this case on this carbon, and replace that now with a CH2. So now I have 1 H on that carbon here. When I treat this with Wolff-Kishner conditions, I replace the carbonyl with 2 H's for a total of 3 H's. Replace the carbonyl oxygen with 2 H's now for a total of 3 H's, 3 protons now on that carbon. So a saturated carbon from the carbonyl reactant. G asks us, where's G? G says, what happens if I treat phenylacetaldehyde with this compound here, this triphenylphosphine with a double bond to the CH2? And this triphenylphosphine with a double bond to a CH2 is equivalent to or in resonance with the reaction that I can do where I have a P plus and a CH2 minus. Let's see if we can figure out how to put that on easily enough. P plus and a CH2 minus, okay? Where now I have an ylide. This is my standard ylide for Wittig reactions. And what that does, at least in the first step, is this CH2 acts as a nucleophile to add to the carbonyl. You form an oxaphosphatane intermediate which expels triphenylphosphine oxide, as well as giving me an alkene in the precise position where my carbonyl used to be. So again, the effect here is I take what used to be a carbonyl and I treat it with the Wittig and I exactly get rid of that carbonyl and put an alkene in its place. H asks, let's go to H. H asks what happens if I treat KC, or if I treat my phenylacetaldehyde with KCN and HCN, so this is cyanohydrin formation where the Cn minus forms a tetrahedral intermediate You protonate that tetrahedral intermediate, kick off this cyano group here, okay? So again, this HCN can act as both a nucleophile as well as a protonation source to give me my cyanohydrin product. I'm going to end this particular video here and then give you more videos